Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
In the previous video, a couple of video tutorials actually, we've been working with time series data and specifically relating to our TerraClimate image collection where we have X number of images per month. I think it's 775 images from 1960 to 2022, end of 2022. So there's a time series of image collections for maximum temperature, minimum, whatever the bands are. So we've got a time series. Whether it's a time series for my region of interest as a whole, or whether it's a time series for each of the individual locations. Remember, we have two assets or two tables, our region of interest as a whole, our boundary, meaning the time series average or median or sum for the whole area as a whole. So we assume all the locations are identical. Or we've created 1,000 random points and we created a time series for each of those 1,000 random points. Okay, so we've also, interestingly, I think, worked parallel from Google Earth Engine and Excel. So just to give you an idea of what we're doing in Earth Engine can actually be repeated in Excel. And also, when I do work in Excel, I understand the underlying ins and outs of the modeling much better. So it makes a lot of sense to me if I can replicate what I'm doing in Earth Engine in Excel, because then it makes sense to me. Then I understand the coding, understand what the code actually means, because I can relate it into what I'm doing in Excel. So that is, for me, quite nice and neat, and we showed that we can basically duplicate everything that we do in Earth Engine, we can duplicate in Excel, except obviously the imaging, but the time series part. Now, if you don't want to work in Excel because there are constraints, then I suggest you work in RStudio. Now, we may or may not in the future do videos on RStudio and connecting RStudio with Earth Engine, because I normally follow the process of generating my images. If I generate images, it goes straight to QGIS or to Geoda. If I generate time series in Earth Engine, it goes straight to Excel, from where I do, let's say, basic descriptive, basic graphs, etc., etc. And then if I want to do time series work, I move it straight into RStudio. So that's basically the framework in which I tend to work. But in the starting point of the journey is always Earth Engine, because that is where you generate your primary data. Okay, so that's what I'm saying. I like working with these various applications concurrently, working with them together. It makes sense to me. I know how to integrate them. It works for me. Nonetheless, okay, so as I said, what we were working on in our Google Earth Engine, our script, is generating various parameters or time series parameters or models for our images or our time series. In this case, we're working with maximum temperatures. Okay, we're working with our TerraClimate and we're focusing on maximum temperatures, monthly data, 757 images, meaning 757 observations of either median for my region of interest or an actual value per my location. So we generated the time series. Then what we've done is we've generated a trend to understand what's happening with the trend. And as I said, this we modeled in an R using the coefficients that we've calculated. There's the coefficients. And then we've calculated the decomposition, meaning the seasonal patterns or the seasonal behavior of our time series. And again, we've modeled that in Excel as well. And what we've done in R and what we've done in Excel seems pretty much the same thing. The results are pretty much exactly the same. And we've managed to generate our coefficients for our region of interest as a whole, and then for each of these locations. So that allows you to use your modeling, assuming that the linear trend will continue, because we're working in linear regression models here. Assuming the trend will continue, we can then estimate unknown future maximum temperatures, either for my region of interest or each of the individual locations. Okay, so that's pretty much what we've done so far. So some duplication, but as I said, the results either being displayed as an image or being displayed as a chart. The results are pretty much the same. And as I said, the key to the whole thing is we use your inspector, you click on a specific location, is to generate the coefficients. Remember, if you go into this tutorial, we're working with a simple linear equation, and we are estimating the beta 0 coefficient, meaning the constant coefficient, and we're measuring the time coefficient, the beta 1 coefficient, for each for my region of interest as a whole, or for each of the locations. And then there's an error term, or depending on your model, it's the error term and the seasonal term could be the same thing. So this is pretty much what we've been working so far. Single regression equation, only time, not a multiple regression, etc. Although you can add additional variables. As I said, you can list independent variables there if you have. For example, if we have minimum temperatures, you can add it there, etc. So you can do multiple regressions, and that's something that we're going to do in some upcoming videos. So we've basically realized that, or we've basically told one another that maximum temperatures has a seasonal pattern. Okay, there's some seasonal element to it, so it's got a trend and some seasonal variation. We said the seasonal variation is a constant variance, it's mean reverting, it's stationary. The trend is not stationary, it's upward trend. So what we can do further, we can generate a harmonic model. So we can now model the actual data. Remember what we've done up to now is linear modeling, okay? Constant in time, that's it. Now what we're going to do is apply a non-linear model, and that's called a harmonic model, and it's specifically related to seasonality, the Fourier sin con cos sin modeling. Okay, Fourier sin con cos modeling. And so this is basically what we're doing. We're actually modeling not the trend per se, but the seasonal patterns around the trend for my variable. And the basic equation is this one here, equation 3 in the tutorial, where we have the model itself, the fitted values, PT, which is our fitted values, and our first two is exactly the same as the linear modeling. There's our constant and there's our time. Okay, so these two are the same as we've done up to now. But here we have two additional variables. We've got a cost variable and a sin variable. Now, it's still based on time, but in this case, we take cost of time, and here we take the sin of time. You see there the T and the T. Okay, so we're still working with the time variable, but we're now applying a cost function to my time and a sin function to my time. Okay, so that's important, and obviously your error term. Now, in this case, see the formula? It's 2 pi multiplied by W multiplied by T. Okay, so the T, so we'll get to the W a bit later, but the W is the number of cycles in a specific period. So if we go, where do we go? It says here, for the fitness model of times here, said W is equal 1 cycle per unit time. Okay, so that is your, okay, so we'll explain it when we look in the graph. So just remember, we have a W here included as well, and that's actually a parameter that we can easily change in our modeling. Okay, so remember, our cost is still a function of T, our sin is still a function of T, but it's not T in the pure sense like in here. In our case, we take T and we multiply it by 2 and pi. Remember, pi is what's 3.7. What is pi? 3.7 something something. And then we multiply it in our case. The W is your cycles. We assume it's 1 for now, and we generate that coefficient. Well, we take the cost of that, and then we generate that coefficient. And here we take the sin, and it's 2 times pi times W, which is 1 times T. And we sin that, and we get the coefficient. Remember, time in all three cases is a value. Okay, so if I go back into Excel, remember, in Excel, if I go here, remember, it's a value, a date value, not the date per se, but the date converted into a value. So, for example, if we go into our model, so it will be B0, which we'll calculate, times B1, and our time is, in our case, the time would be 21916. 21916. So it will be coefficient times 21916 times B, the coefficient, times the cos of 2 times pi 3.7 whatever times 1 times 2.196 plus the coefficient times sin times 2 times 3.7 times 1 times t, which is, what's it again, 21916. So that is my equation, obviously in the unknown error term. Okay, so we have now 4 coefficients that we're going to work, 1 coefficient on constant and 3 coefficients based on time, and 2 of those 3 coefficients, or 1 coefficient is in absolute terms, 1 coefficient is in cost terms, and 1 coefficient is in sin. Okay, so cos and sin. Okay, so I hope that makes sense. That's the equation that we're going to do, harmonic. And the idea is to mirror the seasonal patterns. Remember, if we go into it, our console, you'll see there's the seasonal patterns. Okay, so idea is to model our seasonal patterns. Okay, around this one, to model the observed data, meaning the seasonal patterns around the trend. Okay, so that's basically what we're interested in actually doing here. Okay, so let me just quickly, it wants me to upload again, so let me just quickly retry authorization. I haven't used it for the last couple of hours, so it's most probably wanting me to re-log in. So let me quickly log in and I'll be right back. Okay, we're back. Sorry about that. It happens when, as I said, you live in South Africa and you have load shedding. Because when load shedding happens, like yesterday, we had 7 hours of load shedding. So electricity went off at 12 o'clock and it only came back, I think, at about 7 or 8 o'clock. A little bit earlier, about 7 o'clock last night, it came back. So we had 7 hours of load shedding. Obviously, everything goes flat. Not even the sun or the wind can save you. But no, that's, yeah, dynamics of living in a country like South Africa, where you have constant load shedding. Anyway, so yeah, so we're going to do a harmonic modeling. Okay, so remember this in this tutorial. Remember this equation. Okay, so that's what we're going to model in Earth Engine. Okay, that's what we're going to model in Earth Engine. Okay, so this is where we start. We start with our variables. Okay, there's our independent variables. We call it harmonic independent variables. Remember, what's our dependent variable? Our dependent variable is this one here. This is our dependent variable times maximum temperatures. That's our dependent variable. What is our independent variables? Constant and time. Okay, so that's what we've been working with so far. But then we're creating 2 new independent variables, cost variable and a sin variable. Remember, that's that one that we're creating there for B2, for beta 2, and the sin is for beta 3. So that's your beta 0, beta 1, beta 2, beta 3. That's the 4 coefficients that we need to estimate. Okay, and then we generate the 3 time bands, time variables. Okay, so remember, there's our time variable there, and obviously we're going to multiply it by 2 times pi. Okay, why do we do that? Remember, multiply it by 2 times pi times t. Okay, you see there, times, there's a t, multiplied by 2, multiplied by pi. Time, there we said, multiplied by 2, multiplied by pi. What we don't multiply is as with w at the moment, because w is going to be a variable that we're going to be able to change. In fact, here we assume it's 1. Okay, so it's already built in, it's 1. So you can actually just put here multiply by what's it, 1. Okay, let's see if that now runs. Yeah, so we should get exactly the same. So that's now our w, that value there, our w value there. Okay, so obviously you can change that variable to whatever. If we make it 0, if we make that 0, those 2 variables disappear and we get back to our standard regression model if we make the w a 0. Okay, so this is what we're working towards anyway. Okay, so we can basically change that variable. Okay, so that is creating the t variable, and obviously then we're creating our cos and our sin variable. Okay, so there's our bands. It's our time radians bands, which is time times 2 times pi times 1, which is these variables here. And then we just take those bands and we cos and we sin them. Then we take those variables and we cos and we sin them to give our cost variable and sin. So our cost variable is the cos of our time radians. What is our time radians? It's our time multiplied by 2 multiplied by pi multiplied by 1. So in this case, what we're doing here, okay, what we're doing there is we're generating that variable cos 2 pi wt sin 2 times wt, t and the constant. So that's what we generate here. Okay, so that's what we generate here. And now we're adding the model. You'll see there's the y variable, which is basically this thing here. So let's take it out because we model it in here. There it sits. Okay, the length will be 1. Okay, so remember, and I'll show you what's happened with this now. Okay, so you can either put it there, multiply by 1, or you can just put it in there. So here we're putting the model together. Here we're adding the independent variables with the dependent variables. See, there's the independence added to the dependence, and we're using a linear regression. Okay, and as I said, the waves is 1. Within the time period is 1. So it follows the month. So there's 1 wave per month. Okay, we can do it multiple times, but because we're working with monthly, 1 should be sufficient. Okay, so here we're creating the model. So there we're adding these independent variables, B1, B2, B3, B4 with our dependent variable. So that's what we're doing there. And basically we're just running it. We're just running the model. Okay, we're just running the model itself because we generated the coefficients and when we just, yeah, that's I said, we generate the coefficients, we run the model and we map it. Okay, so that's what we're doing there. And obviously we take the model and then we print it. And this is what we're doing here. We are printing the fitted and the actual values. Okay, so the fitted values, where's fitted? There is our fitted. Okay, and we reduce by sum. We've already showed you that sum is the better reducer. There's our fitted values. There's our fitted. There's our actual for our region of interest. And again, we remember this value here. Remember this value here. Okay, that's a scale value. If your scale is too small, it will give you timeout issues, etc. So, and here we use the reducer mean because it's over the period, over the locations because it's for my region of interest as a whole. Ne? So that's why we're using mean here and not sum, because here we use sum for the different images, for the coefficients, I mean. Here we use mean for the locations, because I'm generating this for my region of interest as a whole. And we plot the two, the actual or the observed and the fitted, and we give it a name. And this is what we get. Okay, so we'll get an harmonic model for our observed maximum time series, monthly maximum time series, mean maximum monthly time series for my region of interest. And this is it. Now what's interesting here is you can see that the harmonic, the fitted values, the modeled values, actually has much lower level values than the actual. The maximum values seems fairly similar. It actually models the maximum values quite good, except these outliers or these high values. But you can see it doesn't really reflect the minimum, maximum temperatures, the lower end of the maximum temperatures. It models that not very nice. Okay, so and then as I said, okay, so before we go there, as I said, this is basically what we've done now. Now we can do that also in RStudio. Now in RStudio, we use again, there's the one. Now just remember it's the same data, but it only goes to December 2020, not to 2022. But you can see that there's the harmonic mean, and again there's your cos 2 times pi times t, and your sin 2 times pi times t, which is exactly what we're doing there. What we're doing here. Here. You can see that part here is in R, basically just here. And we run that, okay, and we get generated. Now, you see, there's the coefficients. There's the generated coefficients. That is now for one cycle. Now, if I change that to 2 cycles, let's make it a 2, and I rerun it, you'll see, come on, let's go back again. So I do 1 cycle, I run it, you'll see there's the coefficients. Now, if I do a 2nd cycle in the time frame, I rerun it, you'll see I get a 2 additional, remember there's the intercept and the initial 2, so there's additional 2 coefficients, okay. So now I've got the intercept, there's 3, got the intercept, I've got a 2 cos and 2 sin variables, and you see it's not multiplied by 2 anymore, it's now multiplied by 4, but this is exactly the same. You can see there's a 6.82, that's one, and then the 0.683, there's that one. So 2 gives you additional cos and additional sin coefficient. So that we can then model here. If we say let's make that a 2, and let's rerun it, and it just will take a bit of time. Nonetheless, so it's exactly the same here. So if I run the model itself, you'll see if I run, okay, so we generated it. Now remember, there's my original time series, okay, this should look familiar. You see there's my original, and here's my fitted time series for my harmonic model. There it is. You can see it. So if I generate these 2 time series and I export it into Excel, then this is what I get. I get my harmonic values of the actual values from my time series, and I get my harmonic values. And if I overlay the 2, you'll see in this case it looks very, very similar. But just as I said, remember there's issues with my time, etc., etc. But anyway, so I can actually do this and there is just my residuals. You'll see the residuals is actually fairly small. Anyway, so this is basically what I've done here. Now, okay, so it's not going to give me, let's see if, so let's leave that as 1. And then let's do this and dot multiply 2. Let's see what that now happens, if it works now. Okay, so while we're busy working with that, seems to be, let's see if it works. So that's not 2 cycles, that's not 1 cycle, it's 2 waves in a cycle. Let's see if it generates the chart for me. So I multiplied it by 2 now, okay, so that's 2 cycles. So that will give you, remember that's multiplied by 2. So if I change this now to 2, remember, if I change this to 2, I've got 2 additional cos and sin variables, okay. See there it sits, and still pretty much, yeah, it's a little bit, yeah, it's actually a bit worse now. If you look at it, it doesn't fit the model any better. But there's a two wave option. Okay, so yeah. Okay, so there we go. Okay, so sorry for that. I was just quickly distracted. Remember, I initially wanted to tell you about the coefficients that we generate. There's all the coefficients. Okay. So I can also model the harmonic model that we've just generated on the image as a whole. So on this image, so we can do that both in the time series, which we've done here. Let me go back here, which we've done, and we can also model it on our region of interest as a whole, so that we can generate the harmonic model not just for our region of interest, which is this one, but also for our individual locations. And this is what we're doing here. So we're generating the phase the amplitude for each of the individual regions and locations based on those coefficients that we just created. You see there's harmonic trend coefficients, which is a sin and cos coefficient. Remember, your sin and your cos is your the amplitude and the length of your waves. So that's basically what we're doing in this case. So if I go and I press on any location, let's say this specific location there, and you can see it will give you an amplitude and a wave. Okay, so there's your the 3 bands. So in this case, the red, 0 point green, that's why the thing is displaying green, and 0. But yeah, so have a look and see what actually this amplitude and value is. If you go again into your tutorial, you'll go scroll down and it will tell you a little bit about what you're doing here. Okay, and I said the phase and altitude is the cyclical pattern itself. How long the cyclical pattern is, how steep or how shallow the cyclical pattern is what we're actually modeling in this case. Okay, so that just gives you, so that will give you just the values of those bands per se. Yeah, go through this code, go and have a look and see, play around and see. This is, yes, nice to do, but yeah, I don't know what the value of it is per se, but go and have a look and play around with this. I'm actually don't very seldom use this. I actually in most cases just stop with the model itself, because what I'm interested is the coefficients. Okay, because once I've got the data itself like this, I can reverse engineer it and I can generate the coefficients, etc., etc. Because if I go there, if I click there, you can see there's the fitted value. That's the actual value. Okay, but as I said, for me, I love working in ggplot, in RStudio. So what I've done there, I can also do in RStudio, and this, yeah, I can then generate the fitted data, and I can overlay it with the actual data. I can actually make that 3 as well and rerun it. Let's see what that model looks now. And there, that's model. So I can, you see that one is not statistically significant. But, and so I can also then go into this one, and I can change that to multiply by 3, and we can rerun it, see what happens with our plot now, see whether that's any better than if we use 2 cycles or 2 waves, remember. And again, go and have a look at this tutorial. Okay, it's 1 cycle per unit time. Now, what's a unit time? Is a month. Okay, so that's the cycles per month, unit time. Yeah, so we're just waiting for this. There, the graph is. You can see it's still not too good. Still not too good. So this harmonic modeling needs some work. Yeah, it needs a little bit of work to make it actually a bit better and stuff. Anyway. Okay, so yeah, that's our harmonic modeling within Earth Engine, and how we can duplicate or align it or work with it in RStudio to get very similar results, if not a little bit better results, because it's much, yeah, it's in RStudio. You can do all sorts of other things that you can't necessarily do or want to do in R. The beauty of obviously of R is you can visualize it. You can visualize it per location using this code in terms of the harmonic terms per location. And that, you know, is the amplitude and the phase of it, meaning the steepness. Remember, this is, where is it going now? If you go here, the amplitude is those peaks, and the phase is going left to right, or time, and the amplitude, and that is just to see how good it fits. Okay, so does it fit? So that's just a measure of fitting. Okay, yeah, hope you enjoyed it. Thanks for watching this video tutorial. We still have a bit to go on this. It's some interesting work. I hope you like it. Feel free to leave me a comment. I'll happily respond to it. And thanks for joining me on this remote sensing journey. And until we meet again, see you on the other side.